Oh, it's basically starting. Hold on, just give it a moment. Hello, I'm back. It's been 2 years. That's okay. Um, yeah, I'm sorry. That's my fault. Uh, yeah, got uni and everything. You know what? Let me just post this in here. A bit of my explanation. Oh, I can hear myself. All right, just pause that. Oh, I can hear myself. All right, there you go. Oh wow, 6 viewers. All right, so I got something. That's good. All right, we'll just give it a moment. Yeah. True. True. 2 years of enlightenment.
Hey.
Oh, shit. It's too loud. Give me a sec. Hello. Good to see you. Bog of chess. It's good to see everyone. Okay. I think we'll start. We'll start that here. All right. So, um, it's good to see everyone. It's been a while. It's been 2 years. 2 years. Yeah. Sorry about that. Unfortunately. I'm like, I'm sorry. But 2 years. And I updated my blog for the first time. Completely updated. Updated everything. I've rewritten it to use. So previously, I used Hugo, and that was a major pain in the ass. It's just a huge pain in the ass. Like I hated it. I hated it so much. I hated using Hugo. But I redid it and put it into I redid it and I put it into Bash scripts, Pandoc, and Lua, and SQLite. This is my website now. If you look at it, right, it's literally Pandoc. It's just a big makefile. It's Pandoc, and like Lua scripts, for example. Like here's like my resources, right? Like to do word count, I do this in here. To get like metadata. Oh yeah, so the the way this works is I set up the makefile to set up the dependency tree in a way that it does all the posts first, does all the posts, and then next it does like the category things for that. So for example, if you have a post, right? Let's say you have a post, right? This post. It'll do this first in the make file, and inside the make file, it'll basically print out SQL statements and like cat it into the database. And then here, it'll like cat it into the database. And then when it goes to generate this page, it reads it out here. So like I abuse the makefile dependency tree to get the metadata, the SQL metadata, in the right place at the right time. I mean, it's a piece of shit, really. It's like, but right, this is what like I've said before. I've replaced my piece of like I replaced Hugo's piece of shit. I replaced Hugo's piece of shit with my piece of shit. So this is yeah, it's Markdown. It's like just Markdown pandoc. I mean that's it. That's it. Like yeah. So uh yeah. None have respected the relative links. Yeah, main graph has respected the relative links in Markdown files. Yeah. Yeah, they like so this I've tried to copy like Obsidian Markdown. So for example, in here, right? Uh so like I post like an image. Let me just take a screenshot of something. Here, right? So like I put like an image here. This is WikiLinks format, so it's got the bang there and two braces. So it's WikiLinks format. This is an Obsidian. Um, this is like my streamer mode Obsidian. So I have like a symlink. It only shows the things that I want. So it's only got these two folders. Um, but yeah, so there's the bang there and two square brackets. So Pandoc has support for that, right? Pandoc has support for that. It's called WikiLinks title after pipe. So you get WikiLinks. But what's it called? Uh you get WikiLinks. But yeah, I have to manually go to resources. Go to resources. I have to manually like set up all of this stuff, right? I don't use any of Pandoc's resources things. I literally like go in here, I go image, right? I check is a wiki link, and this is like very brittle. This is what Pandoc does. I check is it a wiki link, and then I handle the wiki link, and then I do all this stuff here. But really, the main thing is resolve URL. So I just sidestep all of Pandoc's resources, and I use their like low level resource management API. That's it. Um, but yeah, yeah, yeah. It's good to see a lot of people back. Thanks. No problems. Yeah, I appreciate that. Okay, so let's actually get started in lean. So, it's been a while. So this is different to what I would usually do. So lean prover, lean prover. So lean is basically a theorem prover, right? If you've heard of Agda Rock, or it used to be Cock, Agda Rock, or Hull, Isabel is high order logic. Isabel Hull, Isabel ZF. So these are basically theorem provers. So these aren't automatic theorem provers. They don't do things automatically. It's manual proving, but they have a lot of niceties to help with that. So for example, right? Oh shit. Let's see it. Let's hope I don't mess this up. Let's just give maybe there's like an example. Maybe there's an example. There's like I've like done some of these. I've done functional programming in Lean. Um, yeah, we'll try and find an example. So propositions and proofs. Actually, I'll take a look at there's a workspace. It does not exist on this computer. Oh, you're trolling me. Hold on. Project workspace. There's like some previous proofs that I've done like before. Oh, this is like it's like the examples. I didn't really do much maths. Maybe that's like an example. Okay, like, uh, yeah, maybe there's like here. Let's just like I don't know. theorem T. Let's just like work with the natural numbers here. What's a nice statement? I don't know, like a plus b equals b plus a. So let's like give this a go. Oh shit. Formalizing special relativity but got stuck. Oh yeah, I think Lean has something like a Lean physics. They have like a formalization project for physics. Yeah. So, um let's say get this right. All right, so this is like a really basic theorem. It's a basic theorem. Oh shit, my camera's probably blocking it. Oh shit, sorry. Yeah, hold on. Let me like move my camera here. Yeah, that's better. Okay, yeah, that's where it should be. Okay, so this is like a basic theorem, right? A plus B equals B plus A. But, um, how do you prove it, right? How do you prove it? So the thing is, theorem provers go all the way down to the axioms. So Lean uses something called dependent type theory. Type theory of dependent types is calculus of inductive constructions. That's the name of it, calculus of inductive constructions. Um, it's what Rock uses as well. Nice to see you, social gummy. Yeah, so so dependent type theory. It's explaining it is it's kind of like it's like an alternative formalization for mathematics, right? This is what Lean chooses to ground everything on its foundations. So in maths we have Z of C, right? ZFC, the Zermelo-Fraenkel set theory. It's the set theory, but Lean chooses to do everything in type theory, which is a different set of types, a different set of rules. It came from I think Russell, Bertrand Russell is the original. Are you the VLAN guy? Yeah, I'm the VLAN guy, but I stopped doing that. Stop doing that stuff. Okay. So to prove this like really basic theorem, I mean, we get stuff in a library, right? Lean provides us theorems in a library. This is the standard library. We get something like this, right? Add com. Oh shit. A B. Oh here. Wait. So in the standard library, we get this, right? Add com, for example, right? And this clears the theorem. So this is in the standard library. We get the natural numbers defined, of course. These are the natural numbers. We get 0, it's the smallest natural number, and then each natural number is a successor from that. So, for example, these are called the Peano axioms. So let's say all the Peano axioms state is we have 0. 0 is a number that exists. 0 exists, but we also define this function, which is basically what's called the successor, and this is that plus 1. But what 1 doesn't exist. 1 isn't a thing that exists. This isn't a thing that exists. But we define 1 by making 1 the successor of 0. That's just how this works. It's an inductive type. I mean, this is a really shitty introduction to Lean. Um, yeah, I really should be doing an introductory stream to Lean, but this is like what I have here is I've been formalizing LLVM undefined behavior in Lean. So this isn't an introductory stream. I really should be doing an introductory stream, but yeah. I mean, I guess. I mean, I'm sorry to everyone, but I guess this is gonna have to go. This is how it's gonna have to go for the next 1, 2, 3, 4, 5, 6, 7 hours. Yeah, it's okay. Bro, the first time I watched you were in high school, I think. Yeah, I'm in my first year of uni. I'm in first year of uni. All right, so the way you prove things in Lean is something called tactics. So to prove something, you're basically manipulating what's called the goal. So this is the goal state. So this is our theorem. We're basically performing manipulations on the goal to basically get to something that we know. So for example, if we what's it called? Is there a way to rewrite? Is there like a rewrite, rewrite, but not? Okay. So after performing this rewrite, so let's actually take a look at what addcom does. So addcom is, so the way these definitions work is this is the name of the theorem. This is the statement. So for all natural numbers n and m, we have that n plus m is equal to m plus n. You just swap them. You just swap them. So this is in our standard library of theorems. So we can actually perform this rewrite. This is an equality. So we will rewrite a plus b here by the theorem, and we'll swap it. N goes to here, m goes to here, basically swapping them. So after we rewrite, we end up with this goal state. And like, hold on, that's just the same thing equals the same thing. So that's just trivially true. So we can clear this goal with RFL, which means reflexivity. Reflexivity is the state of something. Let's say if you have A equals A, this is just true by definition of equality. This is reflexivity. So that's what the RFL thing does. And this clears the goal. That's it. So we have this goal. This is just true by definition. So it's true. And we proved it. Yeah, so we proved it. So this, like the way you manipulate proofs in Lean is by, it's like a backwards proof. You manipulate the goal to end up with something that you want. This is a very terrible introduction, and I understand how terrible it is. I'm sorry for that, but yeah. More importantly, I want to talk about undefined behavior today. Undefined behavior. So let's take a look. Let's actually talk about undefined behavior. So let's go to Godbolt, right? So all right. Let's talk about something that this is like an example that I like to show. So what would you like to do with this statement right here? This is just like true, right? This is just true. I mean, in fact, if you give an example in Lean, you can just like whisk it away. This is just true. So, example, just like theorem. We're trying to prove that x plus 1 is just greater than x, right? Y, I don't know, trivial. I don't know. We'll just like there you go. All right. This grind tactic is basically cheating. Well, it's not cheating. It's basically a sledgehammer, right? This is a very simple goal. I think it's not true by definition, but this grind is basically making the computer do it for you, right? The computer's doing it for you. So this is a true statement. Like this is true, but right? Why is it true? So, and we'll take a look. We'll take a look at what the compiler does. So I know I'm covering this, right? But I'm just gonna put 03 here. I'm gonna put 03 or something, right? And Clang and GCC do this as well. Look, they rewrite it to 1. They rewrite it to 1. Okay, so this is true, but integers aren't they're not what's it called? They don't have an infinite amount of bits. What I'm trying to say is, right? What's that int? Was it int max? How do I get int max? Limits, right? It's limits. Like, what happens if you did this, right? What is int max? What is int max? Int max is the largest number. It's the largest number stored in this type. So for example, right, int max would be let's like open like Python or something, right? Let's open like Python. Int max is the largest part, so it would be 2 to the 32 to the 32 31 minus 1. Yeah, 2 to the 31 minus 1. And the smallest floating point, the smallest number, smallest integer, the smallest int would be this, and be like that. So int, the int type in C, int type in C goes from here to here. Okay, so we'll just put this number in. So we'll just put this number in. This number plus 1, this is going to overflow, right? This is going to overflow. This will overflow to 0, right? Well, I mean, does it? I mean, the question is like, I don't know. Does this overflow to 0? And then we'll like modulo that. This isn't I don't know the spec that deeply, but this will overflow to something much less than this. This isn't true. This just straight up isn't true. So we found an example where x plus 1 is actually less than x. Why? Because there are only 32 bits. You can't put you can't have infinitely large numbers. So the reason why this was true, right, is because in Lean you can have infinitely large numbers. I can put a nat. That's like huge, right? Eval like I don't know, 10 billion, billion, something like fucking huge. That's a nat. That's a nat, right? This is a number that will not fit into the integer type, right? And any big number you can add 1. This is the reason why this is true. This is the reason why this is true. But if you want to let's say with wrapping arithmetic, right? Let's do wrapping arithmetic. Go back to Helix. Yeah, Helix doesn't work with anything. You can't even get Lean. They only just got Lean working on NeoVim. So good luck getting that working on Helix without plugins. Yeah, so let's do wrapping arithmetic, right? So Lean has this, it's called fin. So let's do 2 to the 32. It's basically modular arithmetic. So we're working with signed numbers here, but we're working with unsigned numbers here. There is no fin int. Maybe I'll change this example, but we'll just start from here. So under modular arithmetic, under wrapping, this isn't true. This is straight up not true. Like there's like this is just like something that you cannot prove. Like I think there's like a counterexample, right? Let's prove that this is not true. So not true by shit. How do you do this? Contradiction. How do you prove that this is not true? Hold on. Let me get my my cheat sheet. Let me get my cheat sheet because it's been a while. It's been a while. Let me get my cheat sheet. Oh shit, wrong place. Let's get my cheat sheet. Okay. So if I want to prove a not, intro, of course, yeah, intro. All right. So how do you prove that? How do you prove a negative, right? How do you prove a negative in Lean? You're basically trying to show that, let's say you want to prove not P. This is essentially, I mean, by definition, this is essentially showing that if you have P, this implies a contradiction. Can we derive a contradiction from P? So to prove that P is not true, having P means we did something wrong. We did a contradiction. So we're just trying to prove this, right? So the intro tactic brings in H. It brings in this to what we have, right? This is what we have. This is our context. We have H. This is something that we can use. and our goal has been replaced with false. So we're false now. So I mean, I guess like, shit. I don't know. I haven't done. I guess like, have false, um, have false by just like exact h, and I'm gonna substitute the largest number. I'm gonna substitute like, no, 32 minus 1. Yeah. Does that work? Oh yeah, I want to rewrite. So I want to basically rewrite. How the fuck do I substitute? Oh, I want to okay. This is an unprovable statement. This is an unprovable statement. The way I've written this is basically for all x, we have x plus 1 is greater than this. This is unprovable. Like for all x is not greater than this. I have to prove it for all x. This is not how you set these up. This is basically saying that what I need to put, the not here. So it's for all. This is fin 2 to the 32. There you go. I'm proving this. I'm proving that this statement here, right? This is the statement, right? This is for all x, for all. This theorem is basically saying, since this theorem takes in a parameter, we're basically saying, we proved that if you give me an x, I can return to you a proof of x plus 1 is greater than x, right? This is equivalent to, this is an equivalent statement. I think it's true by definition. The equivalent statement is for all x is a natural number, x plus 1 is greater than x by, I don't know, exact t, right? Oh, I mean, yeah, true by definition. So these are the exact same. So all right, let's try and prove this. Let's prove that this isn't true in general. So okay, how do I even? How do you substitute? How do you like for all? Okay, apply. And then we'll take this number, right? Does that work? Yeah. Okay, we'll just like, I don't know, like have h1 equals this, right? Okay, we have this, right? And then we'll just like, I don't know, is it like, just like simplify that. Like, h1. There you go. So what this simp did is it like simp? Is it like simp without doing this? Anyway, what simp basically did is it reduced this to a contradiction. Is there a way to just like force this like only at simp only? Yeah. Okay. It reduced this to a contradiction because actually, yeah, hold on. I can like is there a way to like conv, let's see. There's conv. How do I simplify like just these, right? Conv LHS H1. Okay. Yeah. So this is basically what simp did is this is our goal state, right? We brought this hypothesis in. We know that this is true. But when you want to prove that something isn't true, you're basically saying that given P, so we have H, given this statement, can we derive a contradiction? So what simp did is it simplified this plus this is equal to 0. 0 is not 0 is not greater than this. Actually, what I could do is I could have like have h2 0 is greater than this by simp at simp h1 or something, right? Okay, yeah. Anyway, this is yeah. So this isn't true in general. X plus 1 is not greater than x. So yeah, we've basically shown in Lean that when you have modular arithmetic, this isn't true. And generally in C, this isn't defined by the standard to be modular arithmetic. This is basically just saying in the standard, if you have signed overflow, this is undefined behavior. And when undefined behavior happens, the compiler can replace it with whatever it wants. It's just that in this example, this is an example of where it fails, right? So num plus num, num plus 1 is not always greater than num, but when undefined behavior comes into play, when it overflows, this is a true statement. So this is like a quintessential example of undefined behavior. So modeling this, how do compilers model this is really my question, right? How do compilers model this? So really, you could not model it at all, because the thing is, it's undefined behavior. You could define addition to always be wrapping, and then this is you can't replace this with a constant. For example, for integers, right? Integers are signed. In the standard, signed integers have don't have defined overflow conditions, but the unsigned values do. So let's actually replace this with unsigned. There you go. So this cannot be replaced with a constant because unsigned integers are defined as wrapping. It's like modular arithmetic, right? Num plus 1 is really just defined as num plus 1 modulo int max. But for unsigned, num plus 1 is really defined as num plus 1, but it's undefined behavior if you have int max there. It's undefined behavior if you have int max there. So how do you model this? So what LLVM does, so I'm not talking about GCC, because frankly, no one knows anything about GCC. They don't state anything. Like you have to be, it's like no wiki or anything, but Clang has this. So how does Clang model undefined behavior? How does LLVM model undefined behavior? They use something called poison. So poison, as I say here, poison is the result of an erroneous operation. To facilitate speculative execution, many instructions do not invoke immediate undefined behavior when given a legal operand. So, okay, let's give an example. So let's say, I don't know, right? You have, let's just define, right? Let's define x plus 1 as, let's just define it. If x equals int max, return poison, else return x plus 1. This is basically how it's defined in LLVM. So for example, let's say if we have x is an integer, right? In LLVM, this x value can be an integer, or it can hold poison. Poison is a special value in the LLVM IR. It's a special value that propagates. So we can extend the set of values for x being an integer. We can extend the set of values saying that if x is poison, return poison. So x plus 1 is defined for all values that x could possibly take. So what is the role of poison? So the role of poison is for actually defining undefined behavior. So this is the most important thing here, right? If you have poison, it is correct to replace a poison value with an undef value. This is a separate value. I'm not talking about this, but this is like deprecated at the moment. So it's correct to replace a poison value with any value of the type. So it's undefined behavior, right? If you do something that's undefined, so let's do something that's undefined. So it's int max plus 1. You do something that's undefined. You could replace this with anything you want. That's undefined behavior, right? That's undefined behavior. What did the C compiler do here, right? What did the C compiler do here? It saw that for all num, right? Num could either be some value that isn't int max or some value that is int max. So if num is not int max, okay, this is just true. This is just a true statement. But if num is int max, this is num plus 1 is poison, then let's just return 1. Right? This is the thought process of the compiler at the moment. So we'll change this to int. Yeah. So if num is not int max, right? This is just true. It's just a true statement. But not if num is int max, num plus 1 invokes undefined behavior, right? Int max plus 1 is not int max, it's undefined behavior, it's not defined by the specification. It can be anything, right? Num plus 1 is poison. So let's just return 1 because we can change it into whatever we want. And this is just true. So this is true. I know I'm using GCC here. I believe they model it the same way. I mean, they must model it the same way. But if we use Clang, it's the exact same. Yeah, it's the exact same. Even the exact same machine code. Oh, shit. Yeah. So how is this actually modeled formally, right? So if you have a value, right? It can be the value of its type, or it could be poison. So in LVM you can replace. So actually, there's some very good blog posts. There's a couple of these, right? So okay, so these are undef. But it's not a very good example. Motivation for poison. Yeah. Yeah, so like the behavior of a program. So if you have a program that violates the language standard, right? For example, this is a program that violates the language standard. I know it's the most simplest. It's a very simple program, right? But there is a case where it could violate the language standard. If it does, we can do something called behavioral refinement. So the rule of thumb for optimizations like these is you can make a program more defined. You cannot make it less defined, right? You can make so you can't introduce undefined behavior, but you can define undefined behavior. I mean, that makes sense, right? What does the specification say? The specification says you can do whatever you want with undefined behavior. So so let's say if you have num plus 1, right? In the case where it's int max, it's poison, so we just return 1, and this is what they say here, right? Behavioral refinement, the compiler assumes the source has no UB. So, for example here, right? X is an indeterminate value. This condition sets X to 3, and then we use X. So, for example, we don't know what cond is, but the compiler can choose let's say it basically rewrites this source code to be int x if cond x equals 3, and then they rewrite it to else x equals 3. You can rewrite this because, for example, in this else path, right, x is poison. Okay, what can you do with poison? You can rewrite it with this, right? So coming out of this, right, after this cond, x is always equal to 3, right? X is always equal to 3. This is called behavioral refinement. So if you have, like, in this else path, x is not defined. X is, we can choose x. X is anything. We can choose x. X is not defined. So it's poison or undef. For all intents and purposes, for the stream, I'm just going to refer to undef as poison and poison as undef. There's like two different values. Like the way it's modeled in LLVM is you have the most undefined thing, which is poison. Something that's slightly less undefined is undef, and then it's just like no UB here. So no one like in the literature, like for example super, which is a super optimizer, um, super 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 and yeah, it's just like for example super doesn't model it. It's like a super optimizer for LLVM IR. It takes in the semantics for that. It doesn't model it, so def is gone. So we're just going to talk about undefined behavior as either being poison or not poison, so it's not undefined. So in this case, right, else x can be anything. X is undefined, so let's just define it, right? We'll just define it. X is 3, so always x is equal to 3. That's basically a thing you can do, which is nice. It's just it's just like a nice thing that you can do. The standard permits, which is like, I don't know, whatever you want to think about undefined behavior. I mean, at the end of the day, um, I think it's fine. I think there's nothing wrong with it. Um, in a language that doesn't trap, for example, in Rust, right? They're gonna put an if statement. If x equals int max, panic. C doesn't want that. For better or for worse. But yeah, C doesn't want that. For better or for worse. So, okay. How do we model this in lean? That's the question. When is that haircut scheduled? Never. Never. Maybe. I don't know. I kind of like this hair. People say it suits me. I don't know. Or people say I look crazy. But all right, how do we model this in lean? So, let's take a look at how I model it. So, well, before we get into that, let's actually give like an example. Language reference. In language reference. So we get something called bitvec. So T. Okay. So we get something called bitvec. Bitvec in lean is basically a model of int. Just a model of int. It's 32. It's like a 32-bit integer. Bitvec2 is a bitvec32 is a 32-bit integer. So like let's say you have a uint 64t. That's a bitvec. That's a bitvec 64. So this models decently a lot of the like semantics in programming languages when you work with numbers of bits, right? This +1 is defined as modular arithmetic, so it just wraps. And this isn't true. Like this isn't true when you have wrapping. So we want to extend this. We want to basically extend this theorem so that this is a true statement. We want to extend this. We want to make this true. So how could we make this true? So let's see. So we'll actually build up our theory in this file. I'll just like copy things out. But we'll build up this theory. So okay. We want to get here, right? We know that this isn't true. I'm pretty sure you can I'm pretty sure you can just like make this like work. Not. You can just like make this. Not for all. Why did grind fail? Hold on. BV decide. What's it called? Oh wait, okay. What's a for all? Okay. Yeah. Okay. So this isn't a true statement, but it can't be automatically proved, and I'm not bothered to automatically prove, like to manually prove it. Okay. So we want to get to here. Like we want to make this true. We want to be able to perform this optimization, right? What is this optimization? You basically want to take this and you want to rewrite it to true. You just want to take this and rewrite it to true always. So can we make this optimization? With bitvec, no way. Bitvec uses modular arithmetic, and a counterexample is int max. So this isn't true. So let's do this. So this is our model of integers. So it's an inductive type. You can think of this as a sum type or a what's it called in Rust? What's it called in Rust? Rust. Fuck. What's it called? It's something, right? It's like it's Rust types. What's it called? What's the example? Enum. So enumerated type. So it's an example of these, right? In enum type. So these are like these exist in Haskell, ML languages, OCaml, Rust as well. But these have an actual representation in the type theory, so you can prove things about these. So what is an LLVM style integer in the IR? It's bitvec or poison. So we want to model. So what do we know about poison, right? We want to model that poison can be rewritten to anything you want, just anything you want. You can rewrite poison to anything. So how do we model that? So I'll show you how I model it. It's a very simple proposition. It's basically this, right? Okay. And then we want to actually export. Yeah. Okay. How do we model that poison can be rewritten into anything? We first we have to define what do we mean by rewrite? Like what do we mean by rewrite? So what we mean by rewrite is the two things about rewrite. If we have x, it rewrites to x, of course. It rewrites to x if you have some value. But if you have poison, you can rewrite it to whatever you want. These are the only two defining things that is captured by the rewrite relation. If you want to rewrite in a compiler, you take the left-hand side and you can only rewrite it to the right-hand side if you're rewriting it to itself, or if undefined behavior happens, you can choose the behavior. So that's it. This is entirely formally what compilers can do. So, for example, what you can prove is you can write this theorem, right? What you can prove is you can prove that I don't know, poison. You can rewrite poison to 1. How do you do this? Oh, everything with a T1. Okay. You can rewrite poison to a bit vector of 1. So I'll make this like what's it called? This is an IN32. All right. So you can basically rewrite poison to 1, for example. You can rewrite poison to 1, a 32-bit integer 1. So you can do that. How? Well, it's just by definition. So rewrite poison forge bitvec 1. is expected. Oh, yeah. Yeah, so you can just do that. Okay, that's it. So this is true. This is true by definition. So if you have undefined behavior, you can rewrite it to whatever you want. So I mean, there's like another theorem, right? You can just rewrite this stuff. And billion. Like this is just true. So that's basically captured by undefined behavior. But there's something that is also true. Let's say you have something, right? We're basically saying this is not a true statement. We're basically saying that you can rewrite poison. Yeah, you can write X to poison. Okay. So we're basically capturing the idea of refinement. You're refining the program's behavior. So let's say if you have poison, you can rewrite it to whatever you want because you're starting from a program that is less defined and you're making it more defined, right? Let's say you have a program that is defined, maybe like X, right? And you want to make it less defined. This isn't true. You can't do this. The standard doesn't permit you to do this. And the way we define it doesn't permit you to do this either. So this is just like something that's not true. I'll look up the proof because I have a proof of it here. You cannot write. It's like a proof here. Rewrite here, right? Okay, so I'll look up the proof, right? So poison can be rewritten to anything. So you start with X, right? So let's say you have poison here, and then you want to rewrite it to X. You can do that by definition. So, and yeah, so we did here, right? Exact. You're right. Poison forge. So, and then we have here, right? Values cannot be rewritten to poison. This is just these are like the two defining theorems. So values cannot be rewritten to poison. So if you have a bit vec, right? If you have X, this cannot be rewritten to poison. You cannot make a program less defined, right? And what does LVM say about that? Yeah, I mean, it's correct to replace a poison value with undef value of that type. And then here, right? Where's like refine? Okay, yeah. So this is an essence of refinement. Where's it here, right? Yeah, I mean, this is basically just called behavioral refinement. So if you have a program that's undefined, you can make it more defined. You can define undefined behavior. We have the ability to do that. We're permitted to do that. But if you have a program that is defined, you can't make it undefined, right? Right. You're breaking what the spec tells you you can do. So using this theory, right? Using what we have, in this, right? We'll just get rid of this, right? So I've built up, I guess I think like over the past couple months, I've been like working on this. I guess like during uni, been working on this. It's a model of LLVM, LLVM's integer instructions with undefined behavior. So basically what I've been showing previously. So I have the definition, right? LLVM style integers with a poison value. I have the definition of rewriting, of behavioral refinement. So what do we know about rewrites? A value rewrites to itself, or poison can be rewritten into any concrete value. That's it. And I use notation to define this kind of squiggle relation to mean this rewrites to that. And then we have a bunch of theorems here, right? So poison can be rewritten to anything. You can't rewrite a defined value into poison, right? You can't make a program less defined. If you rewrite to poison, it's the same as, does this create undefined behavior? This rewrites to itself, of course. It's transitivity. This is a transitive relation. Rewriting. If you rewrite two things, they rewrite to themselves, like chained. Yeah, like if you have two values that are equal, it's the same as can you rewrite themselves this way and back the other way. Um, oh yeah, if you have a bitvec that rewrites to a bitvec, it's the same as them being equal, right? But if we have that this side could be poison, it's not really the same. Um, but yeah, basically, I have a lot of theorems in here, um, just from building this up, and I have formalized some of the instructions in here as well. So let's take let's like example here, right? Test lane. We'll bring in in, right? Okay, so let's write a theorem. So let's say like example t in 32. Yeah, so we'll just do adding, right? We'll do like yeah. Okay. So the one thing we need to worry about is that equality is not a thing. Like we don't care about whether or not things are equal. We only care whether or not we refine the behavior. So this is true in general, right? Because for something to be equal, this has to cause undefined behavior whenever the left side causes undefined behavior, and the right side causes undefined behavior whenever the left side causes undefined behavior, right? X plus Y produces a poison if and only if Y plus X produces a poison. Like, this is true, but we don't really care about the equals sign. We care about rewriting. So can we rewrite X plus Y to Y plus X? This is true. This is just straight up true. Even when X is equal to poison, for example, right? Uh, like if you look here, right, eval 32 plus poison. If you add two poison values, the way it's defined in LVM is that poisons slip right through. So if you add two poison values, right, or if you even add a poison value and a definite value, a poison slips right through. So poisons are viral. They're viral in that sense. So if you put so X and Y. If you put a poison for X, right, for example, this is just like these are just poison. Like this poison comes down, and you're basically just rewriting poison to poison, which is just true by definition. It's just true by reflexivity. So let's rewrite. Let's give this a try, right? So let's see. Let's start that. All right. So we have two different theorem statements. So we'll rewrite it like this, right? Okay, so which one of these is true, right? So let's say you have x plus no signed wrap y, right? So let's take a look what the no signed wrap instruction is. Add no signed wrap. So this is an instruction in LLVM. It's called no signed wrap. Basically performs add. It's the exact same as normal add. It's adding with wrapping. But if this sum, so no sign wrap stands for, yeah, no sign wrap. So if op1 plus op2 has a signed overflow, it's poison. So then we have that undefined behavior happens. So if you have int x in C, x plus x and y, x plus y is really encoded as add no sign wrap I32 xy in LVM. It's really encoded like this. if you had unsigned, so if this was unsigned, this would be encoded like this, because the standard defines overflow conditions. The standard defines them. So what is, like, out of these two statements, what is true? What is true? So this side, right? X add no sign wrap Y is more, it's if you think about it, it's actually less, it's more, it's like less defined than X plus Y. It's less defined because this can produce undefined behavior, but this can't, right? This can't produce undefined behavior. It's always defined. Um, given defined inputs, this is always to be a defined value, right? So if X and Y aren't poison, right? If X is actually an integer and Y is actually an integer, this can't produce undefined behavior. It just can't. But if X is an integer and Y is an integer, and you add them with no sign wrap, this can produce undefined behavior. Like you can just create undefined behavior out of thin air. So this left hand side, this is a less defined than this side. So with our rule of thumb, we can rewrite from less defined to more defined. Right? That's our rule of thumb. So generally this is true, right? You go from a less defined to more defined. Generally this isn't true, right? You can't go from something that is defined in general to something that's not defined sometimes. You can't introduce undefined behavior. So what does the standard say? A compiler can make undefined programs more defined. The standard doesn't let you make defined programs undefined, right? That's like the one contract of the compiler. Don't fuck up the code. Don't mess up the code. But if you mess up, they have liberty to change that. That's undefined behavior in general, right? So this isn't true. This straight up isn't true. Because, for example, let's say X is int max, Y is, I don't know, something, right? X plus Y rewrites to Y, this, right? If you substitute these in, you get like int max plus 232 rewrites to poison. And then what do we prove? We prove that concrete values, right? This is literally a value, right? I don't know what value it is. I don't know, like 232 something. This is a value, right? What do we know? So concrete value, a concrete bitvec, cannot be rewritten to poison, right? That means cannot. So not the negation. So this is false. This is just straight up false. Because we proved that this false. So nothing, a concrete value cannot be written to poison. So this is true. This is true in general. This is false. It's false in general. So that's basically like a core thing about optimizations, right? You cannot introduce undefined behavior, but you can define undefined behavior. This is basically everything about compilers. This is what LLVM does, and this is what GCC does, and this is what everything works, right? For example, even Rust has undefined behavior. When it comes down to like data races, for example, Rust does not define what happens when data races happen. No one can, right? But the fact that they define that, we assume that it doesn't happen, means that they're defining undefined behavior. So undefined behavior is everywhere. It just depends on who defines it the most. So another rule of thumb is the more undefined your program is, the more the compiler can optimize it. That generally makes sense, right? For example, if you have a huge function, right, and this function is poison, it's poison for some values, right? You can just rewrite it with like nothing. You can like just delete the entire function. So a general rule of thumb is the more undefined your program is, the more you can optimize. It's a general rule of thumb. So what do I want to get done in this stream? what do I want to get done in the stream? So I gave a shitty example of what undefined behavior is. I really ought to like make a blog post about it. I think I will. I think I will. But what I want to get done in this stream, I think I have like I think I wrote like what I was gonna do. Okay, so go over what this project is even about, and then do some of this stuff. So you've got me for a while. You got me for a while. So yeah. So if you have any questions, you can ask me some questions. But I'm just going to be working on some stuff while I'm talking, and then also go through some of the code as well. Go through some of the code as well. So, all right. So let's just take a look at what I have so far. So I've basically modeled most of the integer instructions, right? Not most, actually, like barely any. Like, well, I've got addition, subtraction, I've got comparisons. Um, these are comparisons. I've got like nice notation for that. So, and then I have like and or not. Okay, the bitwise. I got shift left, shift right. I think arithmetic shift right, and then division. I don't have multiplication. It's just a matter of me writing it. Yeah, so I have these instructions, and they interact with the definition of IN. How do I actually define these instructions? So what does LLVM do? LLVM says that poison is viral. So, what's poison? Okay, so most instructions return poison when their argument is poison. So poison's a viral, it's viral, so it passes through everything. So if you have undefined behavior in a sub-expression above, that undefined behavior is going to affect everything that comes down. Um, that's just how, that's just what we're permitted to do. And that's really how these operations are defined. So, for example, this is add, right? This is how add is actually defined when it has non-poison input, so A and B is bitvec. You just perform add, right? And how does bitvec implement add? Pretty sure it's like bitvec add. Oh, okay, bitvec implements add by basically converts x to a natural number, converts y to a natural number, adds them, and then does modular arithmetic, right? The bit vector value I mod that. So just modular arithmetic. So add basically coincides with the add instruction in LLVM, right? You add them, it wraps them. But add no signed wrap. Oh yeah, so yeah, add is also defined as passing poison values through. So it's not enough to define what add is for concrete values. I use this thing called pbind. Like it's called poison bind. Uh, it's like my way of not using monads. Because you can use monads to define this. But really, what this thing does is it's basically a function that this is pbind. It's basically a function that says if x is poison, return poison. If it's a bitvec, call the function on the concrete value, right? This takes in a function which takes a bitvec and passes it straight through. So what pbind does is if x or y is poison, return poison. If not, call the function on the actual bitvec value. Okay, so how is add no signed wrap defined? It's very similar to add. If you take in two concrete A and B bitvec values, it checks, is there a signed overflow? Returns poison, else performs the actual add thing. Same for no unsigned wrap, there's uadd overflow. Same for no wrap, NW is S add overflow or U add overflow. Both do poison, so it catches more. Um, and it's basically more of the same for sub as well. So yeah, this is how these things are defined, right? So I've defined LLVM instructions. So we can actually go into I think take a look at these theorems, right? So rewrite is what you've seen before, and I've got a couple of these like basic theorems, right? Poison can be written to anything. Values cannot be rewritten to poison. Um, and then I also have rewrite if and only if. This is just like rewrite back and forth, right? Can you rewrite x to y, and can you rewrite y to x? That's also there as well. So this is kind of a useless file. So most of these files. So I've been working on this project for since the 9th month. What month is that? September. I've been working on this since September, right? Since September. Basically a bunch of stuff. So most of these theorems are like junk. I really need to like clear everything up. Most of these are junk. Um, yeah. So when it comes down to here, right? Where are the like ideal? So where are the theorems that like I actually have? Okay. So these are some of the theorems that I actually have so far, right? So x plus no sign wrap is 0. You just rewrite that to x. You can do that always in general, because we can take a look at the proof state, right? Take a look at the proof state. So we can do cases, right? We have two cases. So case x is poison, or case x is a bitvec, right? So we'll just do like, instead of actually doing this, right? We'll do like case bitvec, case poison. Okay. We want to unwrap the definition. We want to like unwrap pbind as well. Yeah, okay. Yeah, if we unwrap by the definition, this just becomes like it'll just like simp really. It'll just simp a lot. So it'll basically bring everything down from to just a to just x plus no sign wrap 0. It'll basically like add x and 0 in the congruent representation, and then this is just equal to x. So when you basically simplify, this basically performs a lot of the simplification rules for unwrapping all of this like notation like bloat. Once you simp these away, this just becomes true. And if x is poison, this is also true, right? I mean, because this creates undefined behavior. If you put poison into something, poison comes out. So this is also true by definition. So you can just simp these. So this is the way I prove is really by just doing a whole bunch of proof automation. This just runs a shit ton of like theorems to solve these goals. I know I'm not manually doing all these proofs. Frankly, I don't know how to manually prove these things. Well, I do, but I haven't given it a shot. Because the way I write my notation, it's like kind of really like fucking bloated. Like I'm really like I think I'm gonna do it this stream as well. I'm really in the need of making a lot of these definitions like amenable to manual proving, like manually going ahead and manually proving these things. I think that's what I'll do this stream, right? This is what I'll do this stream. Um, so yeah, but right now, all I really support, like the nice way of proving, is really you just do this. It's just automatic. It's just automatically proving these things. It'll unwrap it to the definition. So this is what I think I'm gonna do this stream, right? I think I mentioned Yeah, work on the general theory of no UB, well formed. Yeah, rewrites. Okay. There's like the last thing, right? I think I proved these. Yeah. Okay. This is like a good example. Okay. Root 2. Not this one. It's a rewrite congruence. Okay. So I do have, so I know I did say it's not really amenable to manual proof, but I do have some ways to manually prove some things, right? So I've written some like custom tactics on my own. So these are like you can write in Lean's metaprogramming language. These are like elaborator. This is just like Lean metaprogramming. I wrote my own tactics to do most of these things. So what does OPT rewrite do? What does opt rewrite do? Um, Basically it performs what rewrite does. So the rewrite tactic in Lean, it basically does perform rewriting. Of course, it's in the name, but rewriting only works based on equality. It only works based on equality. So, for example, in our nat com, in our nat add com example, what rewrite could do, the rewrite tactic, it could basically rewrite n plus m to m plus n, right? It swaps them, right? It performs a rewrite based on equality because these are just propositionally, mathematically true, right? But this, right? This isn't equality. These are not equal. These are not equal. Mathematically, these are not equal. These are only related by a rewrite, by this rewrite relation. These are not. This is not true. Like, uh, for example, right? I think I showed before. Poison and poison and this value. These are not equal. These are not equal things. But you can rewrite them to each other. So this is like a coarser. This is not equality, right? So we cannot use the rewrite tactic here. You cannot use the rewrite tactic here. But I created my own. So this is something called opt rewrite. Let's say it rewrites this theorem here. So I mean, what we want to do is we want to rewrite x plus no sign wrap y to this, right? We just want to rewrite. We want to do this, right? So we rewrote. So this is the original tactic. So this is what we start in, right? We start here. So we have x plus y plus 1, y plus x, right? After performing the rewrite, we end up here, right? And this is like, okay, something on the left-hand side is equal to something on the right-hand side. These are the exact same. What is that? Reflexivity. That's true. That clears the gap. So we do this, right? And there's two different types of, so RW is basically rewrite plus reflexivity at the end. So that's why, like, if we write it more explicitly, it does like this. So how is rewrite implemented? Rewrite is implemented very similarly to how RW and rewrite is implemented, but it just doesn't operate on equality, right? It doesn't operate on equality. Why? Because these aren't equal. This is not true, but we can rewrite one to the other. So I had to write my own tactic. So to do this, right? Let's actually try and yeah, so here, right? We want to use this theorem that we defined up here. So what is this theorem? This theorem is basically saying x no sun wrap y, y no sun wrap x. I prove this by using simplification, and then I use something called BV decide, which basically uses a SAT solver, right? So I really use the biggest kind of sledgehammer possible to prove something so simple. So when I mean it when I say I have no facilities implemented yet to facilitate like manual proving, because this is like the way I like define the instructions is like all fucked up. Uh, the only way to prove these things is to like get an automated decision procedure to prove it for you. So I really need to do this. I've been writing down some notes on like how I want to facilitate like manual proving. For example, like I've done this, right? You get OPT rewrite so far. Um, but yeah, this is proven by the computer, but we can still use it. So we put OPT rewrite here, it rewrites this thing to this thing, and okay, it's just A rewrites to A, of course, it's just true. So reflexivity clears the goal. So that's basically all I have so far at the moment. So I have like a lot. I have a lot of I have a lot of like random like stuff. Like this is a really messed up repo. This repo is like really messed up. Uh, yeah, I've got like stuff I need to get rid of like a ton of this stuff. Like this is like an attribute that I defined, but I like deleted it. I deleted the code for it. Yeah. All right. So let's see. Like, what do we want to do first? Conversions and rewrite super easy. So what was that? What was the last thing I was working on? What was the last thing I was working on? In here, right? Yeah. Yeah. So I want to be able to. So what I'm trying to work on, what I'm trying to work on right now, is I want to convert goals of the form x I and n, right? I want to convert goals of the form of this, right? Rewrite to x. I want to like y, right? So let's say like I have this, right? I want to change this into this goal. I have this theorem. I want to change it into this. So to change to change so let's say I have this, right? Let's say I have a rewrite. F is just some function, right? You could think of F as uh, just like some expression in terms of X. This is some expression of X. We rewrite into some Y. To make manual proving easier, I don't even want to have to think about undefined behavior. I don't even want to have to think about it. So I want to convert goals like this into goals like this. So goals that take in only concrete values and f of x equals y. So for this to be true, for this to work, for this to be true, for this to work is one, y is never poison. Y cannot have undefined behavior. So I guess this is straight up untrue because y can be anything. Based on this, I think I'll change this to be how about this one? F of g. Yeah, right. Okay. Some expression in x, some expression in actually I can remove y then. Yeah. Yeah, so some expression in x rewrites to some expression in y. If you want to prove this, I guess it suffices to prove that some expression in x equals some expression in x. Here, right? Some expression in x, some expression in x. It suffices to prove this, right? When can you transform this goal into this? F of x is never poison. So this doesn't introduce more undefined behavior than if x was poison. Poison for x not poison. And g of x is not poison. It's not poison. So what are these basically saying? F doesn't introduce more UB. These don't introduce more UB than what is passed into it. So I guess what's it called? This would be like a really nice theorem to have, because let's say you have an expression, right? And you know that, okay, these don't produce more UB than necessary. we can just redo these. Or so these don't produce UB at all, more UB. Or you can change this to f of x produces poison. Okay, so these two, this is a more restrictive condition. This is a more restrictive condition. This condition like suffices for converting them. What does this condition say? This condition says that f of x produces poison exactly when g of x produces poison. So these produce undefined behavior at exactly the same times. So if we know that this is true, this might be harder to prove than this, but this admits more expressions we can use it on. If we show that f of x is equal to poison exactly when g of x is equal to poison, you can also do this, which is nice too. I think this is what I was working on a bit yesterday, but I stopped. But I think I want to work on this, right? This is what I'll do for the next while. So for the next, yeah, this is what I do. This is what I'm gonna work on. Mm. Give me a moment. All right, so let's get to it then. Yeah, so I want to remove like this is just like a bunch of crap. I really need to make like a file for this. Let's just like do this here. I'm just gonna be this is like templating. So what do we have? Yeah, this is like the theorem I wanted. So this theorem is like crap. So let's write it. So really f is some expression in x. G is some expression in x as well. And what is the condition that UB equivalent, right? These produce UB exactly when that produces UB. What is the definition? What should I define this as? Yeah, for all. So this is polymorphic on bit width. So for all x I in n, f of x equals poison, and only if g of x equals poison. Okay, that's equivalent. So I mean, if we have this, right, we want this is a hypothesis. We're just gonna take this in as an hypothesis. So okay, we have an expression in x, and we have that they produce ub exactly when the other one produces ub. We can also this doesn't introduce more ub. So this suffices to prove this. I'm pretty sure. This suffices to prove this, but this is not equivalent to this. This is more of a well-formedness. And this is more of a UB equivalent. I mean, does this imply? Yeah. All right. So let's see. And what's the actual theorem statement? Implies. This might be an if and only if statement as well. I actually don't know. Oh, this is not IM. This is a bit back. Okay. So, yeah, this is gonna take a while. It's gonna take a while. Me proving this. Can I move this out? Because this statement, right? This statement is not equivalent to this statement. But I guess I don't know what statement is stronger. This statement, right? Oh yeah, I should probably that. Yeah, so this statement is not equivalent to this, but I don't know what's stronger. Let me just think for a second. I guess these are still both provable. But can you move the for all outside? I actually don't know if these are equivalent, but I'm just gonna go with this definition because it's simpler. Maybe someone can let me know whether or not these are equivalent. But basically, what I'm trying to prove is this. So okay, let's see. So intro. All right. So we already have. I mean, guess it's just makes it easy to just go by cases. Okay. So in the case where they're poison, I guess I'll just handle that first, right? So in the cases where they're poison, by the UB equivalent proposition, this produces poison. Never that produces poison. Okay, so we have this as true. So we can do a cases on I guess we'll just case bash really. Cases F poison. Yeah. Fortunately, this is what I'm gonna be doing. I mean, I'm pretty sure I could like use grind as well, right? But I want to manually prove this, like simple. I don't know. Okay, I guess, yeah, I'm just gonna manually prove this. It might not be the most elegant proof, but whatever. So in the case where there's a poison, wait a minute. How do I do cases in the hypothesis? How do I do cases in the hypothesis? I can do by cases on the actual assumption. All right. Constructor. Constructor AS. Poison equals G poison. Maybe this is unprovable. Maybe this is unprovable. I mean, it seems possibly unprovable. I'm put some music on. All right. How do you obtain H1 or H2? Maybe like because this is an inductive type. This is an inductive proposition. Yeah, I don't know much about it's been a while. It's been a while. It's been a while. Where is it like? Okay, like cases. Whoops. Wait, tactics. Okay. Because even though that's not really a type, it's more like an inductive proposition. So it's like yeah. Maybe I'm blind. This might be unprovable. I actually don't know. If you think about it, if you put poison into this, it should. Yeah, I think this is unprovable. So generally, this statement here. Uh, so this statement. If you have some expression in x, right? F is a function, so f of x is some expression in x. Um, to show that this is like, generally, this is some expression x. Generally, if you have a poison, this should just be poison. Poison should pass right through. Um, this is what I would call well-formedness, even though this is got nothing to do with well-formedness. Because, for example, you could define f of x is equal to that, right? If you put poison into that, like that's not poison, that's 1. So it's got nothing to do with well-formedness. But I guess it's an assumption that I take in. Because I'll show you where I use this assumption. Conger app, right? This is basically the entire thing behind how rewrite works, OPT rewrite. RW and OPT rewrite. Basically the like driving force behind it. If you look at it, it's called congruence. What is congruence? Congruence is basically, let's say if you have like x is like congruent to b, if you have this, it's kind of implied that if you add 1 to both sides, they're still congruent. This is kind of the idea of congruence. It's like an algebraic kind of property. So here, it's called rewrite congruence. So this basically takes in a function f. Really, this function is could be just be thought of an expression in terms of x, right? So this expression in terms of x is so given this expression, given a hypothesis that a rewrites to this new a, we have that f applied to a rewrites to f applied to the different a, but we know that a rewrites to a. Like this should be true. And it's only true really if we take in well-formedness. I guess this could be adjusted. This could be adjusted to be something else. Like this is poison for x is not poison. Like I don't know if this is like. I don't know if this is too strong of a thing. I don't know. This seems too strong. Because for example, right, this you wouldn't be able to use this for where f is this, right? Even if you have f of a rewrites to f of new a. I mean, this is just true because I mean, this is just like one rewrites to one, right? But this does not satisfy this. So maybe this is too strong. I think it's too strong of an assumption. But I don't know what to put. I don't know what to put. Really, I'm gonna have to do a lot of thinking about what to do. But this assumption here, is yeah, I don't know if I'll have to do like add this as well. For example, def well formless. This isn't even well formless. I don't know why I'm naming it like this, but it's basically saying for all. Oh no, f poison was poison. I'm pretty sure like this does not imply this. Neither these imply each other. Let me just think for a second. Yeah. Yeah, I mean this might be too much. I mean I'm gonna have to just think on it. F. Yeah, this might be too much. I'll be honest. This might be like too much of an assumption. But I mean, I guess whatever. Rewrite WFF. Rewrite WFG. What? Oh, does this prove it? Oh, I mean, I guess it does prove it. Right, because rewrite. Right, what do we end up with? We end up with a goal which is poison equals poison. So I mean, this is just true by assumption. Like, well, not true by assumption. This is just true. Okay. All right. So the bitvet case. So, bitvet A. I'm pretty sure I can prove this like by taking cases on whether f is. Surely there's like, what I'm looking to do is I really want to do take a cases like cases f of x. Alright, case bitback. Case poison. I swear to God I can do it this way. Well, by contradiction, right? If g of x is equal to a bitvac, well, I mean, I guess g of x is not poison, but then we also know that f of x. I mean, what are we even trying to show? I mean, like, I'm just getting lost. What the fuck are we even trying to show? Okay. How do I substitute? Why can't I take cases and it show up in assumptions? Ah, yes, okay. This is how you get the assumption. Okay, so we get this, right? What do we know? We know that we have, if we have a bitvac. This is the same as do we not have bitvac? I don't think we have I don't think we have a proof. Here it is. So if we have a bitvac that rewrites to something, that's the same thing as y is equaling that thing. So I want to apply this, right? I want to apply this. God, this editor is like slow as shit. I want to apply this, so rewrite. The assumption is what we have, right? We want to rewrite with a x AS, right? This is in the namespace of rewrite, right? I hope not. Fuck, it is. Did I do it right? What type does this have? Pivec A. I want to rewrite this at. That's AS. Type does this have? I mean, what am I doing? I'm just taking like this, right? A. Oh, this is G of X. Yes. Okay. Good. And then what do I have, right? I have G of X is equal to bitvec of A. So then I can just rewrite AS. That's it. Okay. Okay. So that's one of them solved. I mean, what did I do? I got this right. AS, right? I transformed this into this, right? I just took the if bitvec rewrites, if your concrete value rewrites to something, right? There's no UB on the left hand side, so the right hand side must have no UB, which is the same as saying these are equal. So there you go, and then you can basically substitute this coming down to here, rewrite this with AS, so AS comes in. It's just bitvec A equals bitvec A, right? Rewrite, right? What is that? It's just bitvec A equals bitvec A. What is that? RFL. That's just true. Reflexivity. Okay, good. What do we know about what do we know about this? Well, by UB equiv, if G of X is poison, then F of X is also poison. So I want to rewrite UB equiv. How do I use the goal? Oh, okay. So we know this. We know that this is true. We want to show this, but we know this is true. So we want UB equiv. We want to like rewrite. Well, actually, we don't even need UB equiv. We might not need UB equiv. Hold on. I'm gonna try and not use it. I want to rewrite H1 at AS, right? And then poison rewrites to wait. Yeah, poison rewrites to this, right? What do we know about if poison rewrites to something? What do we know about that, right? Poison rewrites to something implies that, yeah, this one, right? Poison rewrites to something implies that that equals poison. So okay, rewrite. if and only if AS. AS is. Where am I rewriting this at? Oh wait, no. I'm rewriting this at AS, right? Oh, I mean, I should really change this to not taking an implicit parameter because it can't find it. Oh wait, no, sorry. I'm thinking completely wrong. I'm thinking like absolutely completely wrong. Yeah. Some poison rewriting to something is just saying that we can just like make this anything we want. Sorry, I thought it was the other way around. So it's just like exact. We want to like. Oh wait, no. So this isn't a thing that we can't prove the goal from AS. This is just like a tautology. AS is a tautology. It's just true. Well, okay, so we have to use UB-equiv here. So we have no choice. So what does UB-equiv say? So we have this X. H1. How does it work? I want to use UB-equiv, but I don't know how to make that work. Can't I just like pass in an X? So I have this and I want to extract Oh, I'm using the wrong thing. I'm using the wrong hypothesis. Fuck. I'm not even this is a definition. Here, this is the right one. So this is yeah, or I can just take the other way around. Was it NPR? There you go. Modus ponens. Okay. I mean, yeah. So that from UB of X, right? Based on this I guess here, right, this hypothesis. Do we even use H1? Yeah, oh yeah, so we use H1. Wait, this is unnecessary. Yeah, okay, this is unnecessary. Wait, does this actually prove the thing? Yeah, okay, so this, and then exact H1. Yeah, I'm really thinking that these assumptions are too strong. Oh, I don't even use these. What? Okay. I don't even use these well-formedness assumptions. That's great. So they are too strong. But I mean, this is too... Oh, wait, okay, this is like the just right amount of strongness then. Okay, Okay. So if we have, let's actually try and use this, right? Let's say we have let's say we take here, right? Let's say we have INN, we're taking the bit width. And then this is, I mean, what are we trying to say? We're basically trying to say x plus y rewrites to y plus x. So, okay, we want to say that this is equivalent to plus y equals y plus x. I mean, that's what we proved, so we'll just go and use it. Is there like apply t? Oh. I mean, I guess it worked. Oh, okay, so apply t. Okay, we applied it. We just need to prove that this is true. Like UB equiv is true for Huh, it did a very good job of like extracting the thing. What was I trying to say? Saying that these two things produce UB exactly when. Oh, okay. I mean, I guess you can just like show this, right? That proves it, right? Okay, so it's still not proven. Okay, what the hell? For all x plus s equals poison if and only if x1 is equal to poison. Okay, okay, we'll like just like unfold, and then we'll put like a y in there as well. We'll do like an intro y. Where the hell is this? That's just not used anywhere, is that? Okay. More like simp. Okay, x plus y equals poison exactly when y plus x equals poison. Well, these don't ever equal poison. And I really like need to add some simplification rules. Like for example, what I want to add is maybe like a type class, right? Instance fun something, right? Instance like I don't know, like function x plus y. This is the instance like instance no ub, right? Then we'll say that okay, this can't ever produce ub ever. Oh well, okay. This can't produce ub, so we want to convert this into something that this can't produce more ub than what it's given. I mean, I guess like yeah. You think? Proving this is like really fucking annoying. Why is this like simp in? I'm just like I'm just case bashing the shit out of this. But yeah, I mean, okay, so I apply this, and I just need to prove that these are equivalent UB wise.
But I mean, this is like that's like a bit of a work. That's like a lot of work. But I'm sure there are like easier ways to do this. But I mean, I guess so. So like I apply what we proved. This is really just equal to them being equal. And I guess to actually prove the thing, right? To prove the thing, we have this, right? We can just apply G. Well, what's it called? Uh, hmm. There's a reason why we didn't use a well-formedness assumptions. Hmm. Because there's an equivalent statement. Well, not equivalent at all. There's like, I think I stated this wrong. Because the goal was to turn this, right? The goal was to turn this. For all f of x rewrites to that, right? I wanted to turn this into this. Hmm. Oh no, but that's not right. I mean... Oh, how do I do it? This G1 is like not... This doesn't really help me that much. Because this, right, this statement, x plus y is y plus x, this is really just saying that this doesn't introduce more ub than necessary. So this is basically when you convert this into this, right? What is this? What is this statement? This statement is just saying that whenever ub happens for this, ub exactly happens on this side. It might not be that they introduce this as a state. It might not be that they introduce more ub than necessary. That's this statement. This is this statement. But yeah, this statement's basically saying that whenever ub is produced by this, it exactly happens when it's produced by this. This still includes ub though, because of the arguments. These can be ub. Basically, what I want to do is I want to transform this, right? For example, this, right? If I have this, I want to transform into this. But the problem is, f and g, these take in in, n. These take in that. Yeah. These take in in, n, and these don't take in bitvac. I guess maybe a better theorem to state would be this. Right? What is this basically saying? It's basically saying if you prove this, if you have this,
right? This is equivalent to this. Yeah. Right, if this rewrites to this for all IN values, this is equivalent for them. Like you just put them with concrete bit vectors. Yeah. And then you can add simplification rules for that. Okay. So I could use this statement. Alright, I'm gonna the bathroom. I'm in the bathroom. Hold on. I'm gonna be back. Be back, okay? Give me a moment. How do I like draw? Is there a way for me to like draw? Give me a moment. All right, I'm back. Okay. Um, so this is what I really wanted. So, given this assumption, if we know that f of x always corrects g of x, can we replace it with this, given that they produce ub at the exact same time? Is this provable? I mean, really, like, if we were to apply this, right? Intro h. Um, is there a way to, like, apply something at h? What is the hypothesis anyway? H x um h is a bit factor. Intro x at h? Fuck, I don't. I want to use this, right? I want to use this. Or is it like smart to use this? These statements are completely different. These statements are like completely different. This statement is this, right? But this statement is not this. Okay. So remember when I said remember when I said these things are not equivalent? I'm just pick the easiest one. Yeah, this is like not what I wanted. This is what I want. I want to replace anything to do with this. I want to work on bitvex, please. I just want to work on bit vectors. So this is a stupid theorem. This is the stupid theorem. This is the real theorem. Okay. So what do we know about the hypothesis? We want to go from h to f of x equals g of x. Can we do that? We technically already did. Shit, we already did. Okay, well, I mean, I don't know. Just like, we'll just try it. But we can't intro on x.
We can't intro on X. Maybe we can prove maybe we can prove something nicer, right? Maybe we can prove something nice. We can prove something like different. Right? We can do this, right? For all. Right? For all. This, right? You can take this in. And then we'll just do it to this. Yeah. Okay. We'll give this a shot, right? This is basically saying for all rewrites, since we know that these produce UB, if and only like these produce UB equally, this produces UB only when the other produces UB, we can make this into an equality. So wait, this for all needs to stay here. This for all is like this thing. Yeah. So intro X. We want to apply have h2, have h1 from from hx. Okay, we have these two things. We have these two things. So okay, will you be a quiv basically says that we can just do like cases. Let's do cases, all right? Cases on f of x, right? Okay, so we'll do the poison thing first, right? We'll handle poison. So if f of x is equal to poison, so this h can go, right? This h, like, we don't need it. But this is what we care about, right? h1, h2. So h1, well, we can just rewrite h2 at h1. Okay, we have this. Poison rewriting to something is just a tautology, so that's fucking useless. So okay, so we can just copy this proof, right? I'm pretty sure, right? Rewrite. Well, UB equiv is basically saying that. Yeah, UB x MP, right? What do we get? Oh, and that's exact h2. So that's just true. Because if f of x is equal to poison, g of x must be equal to poison because the undefined behavior is linked by assumption. So then these must be equal because poison equals poison. Okay. Okay. So what do we have? Oh, I mean, we can just copy the above proof. Like, seriously, like, basically, like, really close at the assumption, which is h1. Right? We got this, right? And then we have this at h1. We have this, right? And then we just rewrite h1. Truth. True statement. Okay. So this is the one that we want. We want this one, not this one. Are these equivalent? I mean, probably. I don't know. Uh, is this like a thing? Like, is this like a true thing? For all something, something for all. Like for all implies for all. It's the same as for all. Something implies something. I don't know. I don't know. But we can use this fact. We can just use this fact. So we can convert this T1H, right? Well, what is H? H is this, right? H is this, and from this we can convert this into this proof. Why can't we do that? Oh, T1 accepts arguments. Whoops. T1 accepts a lot of arguments. So F, G, and UB equivalents. There you go. Okay. So then we have this new new thing. So then we can just I think we need well-formedness then. I think we need well-formedness to prove this. Maybe, because I'm thinking how we prove this, right? How we prove, like we know this is true, but we want to deal with the poison case where X is poison. If X is poison, right? If we have f of X, I mean, we know that this is poison by the well-formedness condition. Well-formedness condition, quotation marks. And that's easy. That's just true, because they're both poison equals poison. Hmm. Shit. I don't know, man. We basically just need to show that for X is poison, right? So just cases. Cases X. Okay, so we need to Wait, this is this is backwards. This is completely backwards. It's completely backwards. All right, no, I know what's going on. So I know what's going on. So this is just true. This is like just straight up true because we know like from this, right? You can just put a bitvec in. Like you can just do this, right? You can just exact you can just do like is there a way to intro? No, there is a way. There is a way. It's just intro A, right? And then exact h1 bitvec A. Yeah. So, right? Because from h1, you just substitute this into that, and that's just true. But I don't know. Can you use this? If this shows up in the goal, right? I want to convert this. I want to convert this into something on bitvex. But this is just implication forwards. I really want implication backwards. Oh, come on, is it like a backwards arrow? I really want this. I mean, this is just like trivially, like really straight up true. Uh, I guess I'm like getting really bad at writing what I actually want. I want this, right? I really want this. Why do I want this? So if I use the apply tactic, if I use the apply, I want to like, I want to just like apply TT1, right? If I use the apply tactic, it'll convert this in the goal into this. So this is like the hard part. So but it might even be easier. So let's do this, right? Cases. So uh um so well, this just implies that g of x equals f of x. What was the one that we used? If we have bitvec rewrites to something. Yeah, this thing, right? Basically, we want this apply. We want to rewrite. I-N-A. Oh, well, I mean, okay, I just need to write this and it just does it for me. It's interesting. It just unifies it for me. Okay, I just write this. Okay, and then I have okay, and then okay, now I need to show that g of x equals f of x. Is this enough? So we can just do cases on x, right? Cases on x. So bitfac b. Okay. So when they're poison, of course, if you put G of poison, F of poison, this is true by assumption because of UB. So exact UB, what am I missing? GF. Well, I don't have to write anything. Wait, what did I write? What is UB? Oh, UBX. Come on, man. UBX. Oh, okay. I need well formulas. So this I need this, right? F of poison. So what is really the statement of this? What's the statement of this? This statement is saying if something about not observing poison. F of poison is equal to G of poison. I mean, is this should I pack these into one? Anyway, I can just put this in here, right? This is really just exact, well-formed this. Oh shit. Is there a way to reverse these equal.sim? Perfect. Yeah. Yeah. Maybe I should do this on G of X. No, okay. Yeah, okay. Alright, so alright, and then this one. What's this one? What's this one? So oh, this is just by assumption as well, which is really nice. Like, this is like I can't just like write this. No, I can't. So I need to so let's just like rewrite h1. Oh wait, no, let's apply. No, what? How does it even work? What? Apply ASB. Oh wait, no, exact ASB. ASE. Why is that not right? Oh. Good one. So what are we not using? I'm not using UB at all. Interesting. Okay. Well, this is just true. Because I guess exact this is like what's RFL or something? I don't know, like simp. It's just true. There you go. So I didn't use UB equivalents. This is kind of a useless thing. This is better. Yeah. F of x is poison, g of x is poison. Yeah, I mean, really, this like comes to show itself here. So okay, we can convert statements of this into this, given that these are well-formed equivalent, like UB equivalent. Maybe this is like an incorrect UB equiv tac. And this is like really easy to prove, right? This is really easy to prove. Yeah. Okay. Yeah. All right. So let's see. Yeah, I mean, this is really easy to prove. So let's actually give it a shot, right? Let's give it a shot with the example I used previously, right? So theorem. So if I have x and y, and we take in this, and then we have f. Well, not really. Let me just show this, right? We want to show that x, right? We want to prove this. So we want to apply. And then what is case A? Um, yeah. So yeah, so we want we can't really do it with two operands, can we? TT1 yeah, and then intro A, and then not refine, it's something else. Reverse. Then apply TT2 to this, right? Oh, TT1, TT2. Why can't I apply that? Oh shit. What I want to do is I want to remove up all the forals to nothing. I want to like empty up all the forals. Maybe I can have a tactic at the end of everything. What if you have, okay, if you have these things that are equal, these rewrite into each other. So I guess like to use this, it's just literally like exact TT1 WF dot. Right. I guess like what I want is this statement is equivalent to this statement. It's not true the other way around, right? Hmm. Hmm. I don't know. I'm just like confused. I like what I want to do. Right. What I want to do is I want to take this. Right. I want to just like keep reducing and reducing and reducing and reducing. I know that something equaling something else. Like, is this true? Theorem. Um. If x and y, right? Right. If you have that x equals y, this is basically equivalent to. I don't know if it implies. I mean, does it imply? No, it doesn't imply. Oh, well, no, it doesn't. It's not equal, but it implies, right? Implies. Implies x rewrites to y, right? I mean, we literally have this as equal rewrite. I guess put this here, right? So yeah. I guess making these parameters is better. Oh, so you have the intro. Okay. What is that? Conv HS. No, it's better to just do intro. Oh, I mean that's just that's just like easy. What the fuck? Okay. Whatever. Okay. Yeah. So given this, right? Um right, and then we want to apply H. What? Oh no, we want hmm. Is there a way to apply this? Well, the other way around. Oh, this is UB equiv. This is much stronger. I mean, what are the differences between these two theorems anyway? Okay, this is the converse of the other one. So these require different assumptions. This is saying whenever, like, what is the like interpretation of these terms? So like this assumption, we have that this implies this if we know that f and g are UB equivalent, but really what is this? And f says UB exactly when g, right? And then the interpretation of this theorem is basically we have that f of x rewrites to g of x. Yeah, rewrites to g of f of x rewrites to g of x. If we know that f does the same thing, both take in UB, right? I guess what is the like interpretation of these? Legia uses lean. No, he doesn't. No, he doesn't. Legia doesn't. Legia, what does Legia use? He uses MATLAB. He uses MATLAB. How you going? How you going, Josh? All right. F of x, yeah. F of x rewrites g of x implies that their bit vectors are equal if we know that f produces ub exactly when g produces ub. What are the interpretation of these theorems, bro? You still have exams? What? You're kidding, right? You're fucking kidding. You still have exams. No way. Are you really? Oh. Yeah, alright. Fair enough. Fair enough. Fair enough. Fair enough. Alright. Don't worry. You'll do well, because it's just like American shit. It's okay. Yeah, you do fine. Note that f produces ub exactly when j produces ub. Okay, and then I really don't know what to interpret these. Alrighty. No worries. See ya. Ub exactly when g produces ub. That makes sense. That first theorem makes perfect sense. This is when. What is weaker? So, I guess the easiest way to characterize these two theorems is basically showing that like what's weaker. Well, to show what's weaker is that easy. You just need to show that these. You just need to show that these right. These are, you know, Do we have that UB equiv? So this might be. I don't know. I don't. These don't imply each other. These don't imply each other, do they? No, not at all. These are different conditions. Hmm. Yeah. I guess. Yeah. These don't imply each other. These are completely different assumptions. But I mean, the interpretation is like really like this is weak. This is much weaker. This is weaker. This is stronger. But it's just these aren't really equivalent. These assumptions aren't equivalent. Um. So this is the stronger one, right? This is the stronger one. So we'll just like rename these. All right. This is the stronger one. So when they both take in undefined behavior, this is generalized to multiple argument function. I mean, this is the only theorem we should be caring about. This is the only theorem we give a shit about. Um, can you just like simp this away? Oh, you can. Hmm. Because for example, right? I mean, yeah. I mean, what I was trying to show here was this thing is like no UB, right? F of x is equal to poison. Right, so there's like multiple ways to characterize this thing. Um, two left-hand sides. Well, if you put poison into there, you get poison out. So that's just like true. Yeah. And then this thing, right? What was I trying to prove this on? Yeah, so this thing's just stupid. These things need to go. This needs to go. Yeah. It's taking a while to build. Okay, built. Like, I don't... What are the characterizations between all of these? So we know that no UB implies formed. These don't imply each other. Of course they don't. No UB on F. No UB on G. Well, really, this just implies UB equivalent. This is like a very strong condition. It's much stronger. Does it imply the other way? Ah, yes, it does. So really, I guess like the hierarchy of like strong assumptions is like UB is like the strongest. Right? These just imply everything. Well-formedness doesn't really imply shit. It's like weak. Well, well-formedness F. Gee, this implies UB equiv. I guess like I don't really know how to write up a characterization of them. So these don't imply each other. So these can go away. So I guess that no UB is stronger than well-formed. These are like the weakest. These are like the weakest assumptions you can have for an expression. The weakest assumption you can have for an expression is probably UB equiv this. This thing is weakest. But it's weakest, but this is the one we care about the most. This is this needs a much stronger assumption. This is weaker in the sense that, yeah, we want to remove all UB. I mean, do we even need the reason why I'm saying this is because we can remove all undefined behavior on the arguments by just doing this. All right, if you take a look here, right? Take a look at the goal. That's it. Like you can just convert the goal to a bitvet goal. So do we even need these theorems? I mean, I guess these theorems are here because it's just nice. I guess we need to simplify them when we have a bitvet here. It's like if we just do simp, right? This just goes away. What theorems have this? I mean, this has to. I just really want to fucking delete this. This is pointless. Where is it? Simp iron. Here, right? So these get unwrapped to nothing. What I can do, here at least, is here's a subset. This is simp iron. Clean. Simplimus. Okay, so any def without these, I want to add this. I also want to restart as well. I want to add this. And how do I make a simps? I want to make a simp set a subset of another one. I mean, whatever. All right. And then here, I guess this is just right. Simple. I guess like I'm just gonna try and prove some harder theorems and see what happens. Like what I want to prove is associativity. Yeah, I want to prove associativity for this. All right, I want to work to proving. I want to work to prove this. All right, I want to work to prove this. So, yeah. So this thing, I want to work to prove this. So these have the same sign. Yeah. Yeah, I want to work to prove this. So this is the way no sign wrap works in LLVM is, I guess I said this in the beginning, it returns poison if the arguments are poison. That's just how instructions work. But if the two arguments are not poison but signed overflow happens, poison comes out. Undefined behavior. Undefined behavior happens. So
the only way that this is true is if the left-hand side has undefined behavior exactly when the other than the right-hand side has undefined behavior. I mean, basically, this is the only way to guarantee that this has undefined behavior exactly when the other side has undefined behavior is if they have the same sign. That intuitively makes sense, right? Because if you're adding, right, if you have a huge number plus a huge number, so it's huge, huge plus huge, huge minus huge plus 0, right? Oh wait, huge minus huge plus 0, minus huge, and then associativity will, oh wait, no, what's the example? It's like huge plus small plus, yeah, so huge minus huge plus small. And then this rewrites to huge, yeah, this rewrites to this, right? Huge minus huge plus small. Yeah, so this thing doesn't, I mean, these things don't. I'm trying to think of a good example. It's like small. Plus minus small. Yeah, so this causes undefined behavior, but this doesn't. Right, if you do these first. Right, I mean, I guess that makes intuitive sense, really. This plus this causes undefined behavior, it's the overflow. If you reassociate, this doesn't cause undefined behavior, this is just 0. So you cannot rewrite these to each other, because rewriting this to this introduces undefined behavior. It's something you can't do. So yeah, we need to guarantee that these have the same sign. So how do I guess, yeah. So let's just take this, right? Let's convert the goal to a bitVec. Oh shit, that was easy. Okay, we convert the goal to a bitVec. Okay. And then we'll go like intro. This is our assumption. So this does like a terrible job of like naming them. I guess I need to turn this into an actual like metaprogram. So when the most significant bit is set, these most significant bits need to all be equal for them to have the same sign. I guess yeah, that's what I need to have. All right. my biggest issue is that these are just a pain in the ass to work with. This is just a pain in the fucking ass to work with. These assumptions. This thing, I need to like make sure. I need to like make this better. This needs to be made better. Oh, what's the problem? Bad import. We're talking about. Oh, yeah. Well, lemma's gone because it's just useless. Okay. So I need to make this better. This tactic kind of sucks. Yeah, yeah. Cases V. Cases V. I don't know shit about macros. I don't know anything about macros. How could I? Oh, God, that's a pain in the ass. How do I? Oh, this is gonna suck. What I want to do, what I'm trying to do is I want to pass ABC, right? I want to pass ABC to the macro. What the hell? Why does it need? It doesn't need a thing in lemmas. Hold on, I'm just fixing these imports. Oh, oh, of course, yeah. Give me a moment. Get theorems. There you go. I fixed it. I just woke up. Okay. Okay. What do I like? So what is gonna be cancelled, really? So I mean, I did this. All right. I guess it's like a really shitty. I need to do a blog post. Create blog post on this. Yeah, yeah. These are kind of like, I don't know. Are these like this misname? My OPT poison input. So, all right. So like what I need to get done is really I want to support arguments to the conversion. Support arguments to the conversion thing. Then I mean, because like for example, what was the problem? What? Bad import. Oh, the lemons is just like, why would you even need this? Great. All right. So, this thing, this macro,
is useless because it doesn't bind these. It doesn't bind these variables. Um, it just doesn't bind them. So I need to do this. So support an argument to the conversion. Then use to deal with these. I mean, I like really like I really want to turn this hypothesis into I want to turn this hypothesis into something nice, right? Like this, right? I want to turn it into this. Yeah, I want to turn this into this, right? I want to from this. I want to get a is greater than 0 and y is greater than 0 and z is greater than 0. What is this? Oh shit, do I not have... Oh, yeah, these are like terrible precedence rules. And this is greater than 0 or uh or y is less than b is less, yeah, b is less than 0 and c is less than 0. These are propositions. What's up with the triple ampersand? Hi Max. This is bitwise and. It's bitwise and. Um, like yeah, it's bitwise and. So this is and in like C, but this is and in lean. Um, I don't know why they do this triple. I don't know why they do it. It's just that. Because I wonder like what do they use for this? Let me just check real quick. Let me just check. I want to jump the gun. Example eval false true. Okay. So this double ampersand is boolean. This is boolean. This is boolean. Um, but this right. I don't know, like 0. Uh, this is bitwise and right. So this is a 32-bit int 0. This is a 32-bit int 15, right? 0 ANDed with 15. That's just 0 because there's no bits set in 0. That's this. That's this. Yeah. What do you use a single ampersand for? Nothing, I think. I don't know. I actually don't know what it's used for. Nothing. This is just not a thing. Nothing. Just weird. Um, yeah. Interesting, yeah. I've been at it for 3 hours, 40 minutes. But what's it called? When I started there was like 10 people here. And then like within the first 40 minutes it like went down to 1. I think this shit is not interesting. I think this shit is like not interesting at all. I think what would be better is like if I actually like programmed like something, like if I actually did like lean, not lean, if I did like zig or something, if I like programmed that, because this is like yeah,
Well, nobody understands Lean. Yeah, I know. I know. Like, you'd have to be there when it was written. But like I wrote like most of this stuff like months ago. So like I don't even remember, but I'm like learning. But these like the people who are watching, they don't, like this code base is also a mess as well. Uh, what I've been doing for the most, for like most of the time, is just like cleaning this code base up and then trying to classify the different types of conditions on undefined behavior. Like, in the beginning, I think I had like a pretty okay, uh, I gave like I gave like a, guide to undefined behavior. I gave like a guide, like like an explanation. Um, yeah, yeah. So where I'm at now, okay, where I'm at now is I'm just trying to like collect my thoughts for this, right? I'm just like writing down what I need to do. So anything back now. In terms of bitvec, so like this thing, I need to change this to SLT. This is a really annoying thing. Bitvec in Lean, like bitvec, like bit vector. So like if you have bitvec 32, it's like a 32-bit integer. They define SLT, but not GLT. They don't define greater than. Why the fuck would they not? Why would they not do that? Okay, whatever. Whatever. Def, bit, GLT. Does that exist? Is that a thing? Like, yeah, they define this. Like, sign. Okay, they have sign less than. They have sign greater than? No, they don't. They haven't defined that. Why? I don't know. So I guess I can just say, like, not. Right? Not. Sign less than. If something is not less than or equal to, it's greater. Right? Each and bool prop. These are props. SLE. I don't know, man. There's no like nice way to write this. This is a bool, so like I guess like I can just change it to this. Yeah. Okay, that's nicer. This actually works. So SLE. SLT. Yeah, I mean, I guess that's how you translate this. Yeah, Lean doesn't have nice facilities for a lot of the bit factor stuff. Like they just have enough, but they don't have comparisons. So I guess like here is an example of conversion that I want. That should be a thing. And then what else do I want? So when I automatically prove this, right? Be by
guess by a monad. Um. Hmm. Uh, hmm. Everything I have is good for this. Like proving this is like simple. Um, but don't. Oh, hold on. Make it just like simp only. Does that work? Yeah. To further reduce the definition, but don't go further. You need Guzman? I don't know. I don't know. They haven't been picking up my call. They're stealing my likeness with this. Although this isn't really useful. Guzman looking crazy. Oh yeah. Oh, starting to get hungry. I'm gonna eat in a while. In a while. I did write that I was gonna stream for 7 hours. Maybe if I was like doing something else that wasn't lean. Maybe if I was like doing like Zig or something. Maybe if I was like schedule a lunch break. My lunch break's after 7 hours. But I ate breakfast. Um yeah. Well, no, like okay, maybe I can like eat here. The thing is like I'm thinking about like cutting it off. Maybe like do 5 hours. No, maybe do 5 hours instead of 4, instead of 7. What does it even say? Hold on. Um, here, right? What have I written? What have I written? I've written that this goes 5 to 7 hours. Okay. I might I don't know. I think I'm biting off more than I can chew. I think I might bring this down to I think I might bring this down to 4 hours as well. If you cut it off, you're gonna pay us back. No, I'm not fucking paying you, bro. 7 hours. I don't even think I can go for 7 hours. Okay, I can go for 7 hours if
if I was better prepared, you know, if I was better prepared, because the thing is like, this is like this code base is like fucking old. This code base, I stopped working on it. I think I stopped working on it like before. I stopped working on it like week 4. I stopped working on it week 4, and then Flex Week happened, and then before Flex Week, I was working on my presentation, and then Flex Week presentation, and and then like I just stopped working on this. Yeah, I wrote it. I wrote it when I didn't know how to fucking do this stuff. I was just like, yeah. I didn't know how to do this stuff, but I've like been thinking. I've been thinking. Like I know exactly what to do. I wish you'd linked it. It is linked. It is linked. It's this one. It's here. It's here. You can fix it. You can fix it. No reference to YouTube comments. I'll end it all. Oh, that guy. Yeah, fuck that guy. No. Okay, Justin's referencing like some stupid guy in my comments. I was like, I wish you linked your code base so I could fix it, like my YouTube comments. Yeah. How long did I like? This is like a long time ago. Remember, Max? Remember when I was working on like the LLVM like parser in Zig? This is the same. This is the same repo. This is the same repo. The lost genius of the world hiding YouTube comments. No, I think the guys are just stupid. Like I was just like straight up stupid. So, oh well. So I'm just gonna write what I'm gonna do next time, and I might, might cut it off. I don't know, but maybe on this time would be longer, and I might do like I don't know what I should do for variety. I mean, I don't know. I don't have too many projects at the moment. Like this is my like number one. This is like the only thing that matters at the moment. Um, 24 hours of CI. This will get CI later. This will need CI. Um, what else? So I've got this one. I've got this project, and shit, I don't know. So there's a what I've thought what I've like deduced from this, right? Everyone like there are people who want to watch me stream, but no one wants to watch lean. No one wants to. Okay, I want to work on lean, so I'm just gonna work on it. I don't give a shit. I'm just working on it. But like maybe there's like a different maybe there's like a different project I could do. Anyway, by Justin. I don't know if there's any other projects though. Cause like what is it like? There's not much. I might do like math or something. I might do like math or something. But anyway, yeah, I'm just gonna write down what I'm gonna do next. I'm gonna write down what I'm gonna do next. So uh so I guess like it's what argument uses implication numbers to break down to the bit back. So this is like important. So I guess I guess the idea is so you like you can work like okay, you can work with there's like two different ways you want to try and prove stuff in this framework. There's like two different ways, like prove by rewriting based on what you already know. Prove by I guess this is like the human proof. I guess it's like more human. Prove by the of the actual program. There's like kind of like a human proof as well. It's just like automatically proof. So like we have like w- like what at the moment, right? We have 1 and 3. So I guess we need 2. So that's like the most important thing to get at the moment. So I mean, super easy. I mean, I guess so. I guess I did this. Is this a misname? Probably it's a misname. I guess we didn't do this. I guess we're working out that this is a misname. Yeah, so there's 2 things, right? There's 2 things. So it's really like this entire thing. This entire thing is solving 2. Solving 2. And then this is really infrastructure for opt. So it's basically the above. Using a monad as you traverse terms. Preserve. So like this. I mean, what was the thing that we came up with, right? We came up with these theorems, and like UB equiv, like these things. Yeah, proving that these are the same. An instance. Yeah, okay. There might be like okay type. Uh, general type classes for different possible B. So for example, any more UB than arguments, but does. Generally you could have generally like it's just you can just prove that this is just not true, right? Um hmm. Yeah, relating these type classes. Um hmm. Yeah. Yeah. I think I might end it here, you know? I think I might end it here. All right. Yeah. I think that's fine. I think that's fine, honestly. Yeah, I mean it was good. It was a good first stream. Really like what I need to do is prepare for the next one and then see some other stuff. Maybe I do like some like math, like a variety kind of. Yeah. Yeah. But maybe is this what's it called? This this code base gets nicer. It'll be easier to work with and easier to follow. But you know. Anyway, oh man, I'm so fucking hungry. All right, goodbye. Bro, if Lena isn't interesting, the answer isn't doing math. No, okay, math is easier to follow. Okay, let me think. Okay, yeah. Lean is gonna get more interesting. Okay, the code base is shit. I think okay, I need to do I'm gonna do a blog post. I need to do a blog post on explaining this code base. So I'm gonna do a blog post, not about like really explaining it. I said I was gonna do a blog post on this definition of undefined behavior that I've like written here. That's what I said in the beginning of the stream. I was gonna do a blog post. Yeah, I was gonna do a blog post on this definition of UB, and then people can read that, and then maybe it'll be easier to follow. Um, I guess because this isn't like interesting at all. This will get interesting when I'm able to get a program right. I'm able to get a program, and you're like, okay, automatically prove it doesn't have UB, and then okay, automatically optimize it, and then like and then yeah, and then I'm able to like this will get like way more fun when time comes and I can just like go into like LLVM. I can go into LLVM and then take all of their rewrite rules. Just take all of their rewrite rules and just like make these theorems and then automatically prove them. That's when it gets like actually like super interesting. I guess we're kind of like this is like in the shitty stage. I mean, it's always been in the shitty stage, but I guess like when I stopped working on it, um, when I stopped working on it, I got up to like something like this, right? I got up to here, right? Where was the thing where I used like opt? So when I stopped working on everything, I got up to here. Why the fuck is it not working? Unsolved goals. That's additive. Oh yeah. Okay. Got up to here. Let me just copy this. Yeah. Okay. So when I finished, I got up to here, where it was basically I could like this is like a rewrite rule that like you can like swap them, right? X plus y is equal to y plus x. You can just swap them, right? And then what I had was this tactic, which basically allows me to rewrite this shit. Like, for example, in the goal, right? In the goal, I'm starting with this, right? I start with this, x plus y, right? With this commutative rule, right? I can perform a rewrite, and then hold on, y plus x. I just rewrote it. I rewrote it. So then you can see that okay, this is just like a rewrites to a. This is like the exact same. Like this side is literally equal to this. Like this is just true by definition. And then that's it. That's like there, prove it. So that's what I got up to. Automated theorem proving instead of manual theorem prover. Um, well, like this is manual. Like this is all manual. But you can write tactics to automatically do stuff for you. I like a good example is like the grind tactic. The grind tactic is like magic. It like solves anything for you. Um, that's an automatic tactic. If you go to the Lean website, right, they have like this example. Their use case would be applying all this manual resulting work automatic. Yeah, that's the like the like I'm doing all of this stuff. I'm doing all of this stuff to make everything work automatically. So this is like the shitty stage where everything's manual. An example of like an automatic thing is like grind shit, right? Grind just like solves all of this. Like it just solves all of this. Um, the reason why like I would prefer lean over something automatic, some pre-existing automatic to improver. So okay, I was about to say that. I was about to say that. So let's say you're in Daphne, right? Let's say you're in Daphne and you're you're trying to prove something and you just can't fucking prove it for the life of you. You just can't prove it. You're just stuck. You're stuck, and the SMT solver doesn't want to help you, and you just don't know what to do. You're stuck, right? There is no way out. There is no way out, and you can't even like access the internal reasoning of this SMT solver. Right? At least with lean, if everything fails, you can prove it yourself, or you can actually like sketch out the proof. You can like, okay, I'm gonna like manually say, okay, this case, this case, and this case. I split it up into three cases manually, right? And then I say, okay, I'm gonna manually prove case one, but then case two and three, I can just use the automatic prover. At least with like lean, you get that ability to do that. With like Daphne, it's kind of over. It's like it's actually over. Like you just like what the hell are you supposed to do? Nothing. You can't do anything. At least with lean, like all of the automatic stuff is like is opt in, right? This grind, right? This isn't magic. Like this is literally like this is a tactic. This is implemented in lean. It's implemented in lean. Um, yeah, lean to yeah. Like this is implemented in lean, so like everything's opt in. Everything is just like opt in. If you want to do it manually, you can do it manually. This simp here, this simp like applies a bunch of simplifications. If you did this manually, it would be a pain in the ass to just like manually thing. But what simp does is like it just searches for a bunch of theorems and just like applies all theorems as much as it can. It literally applies the first one it can find and just applies a bunch of theorems. Like this is like automatic, but it's like opt in. Everything's opt in, which is nice, right? It's nice. Yeah. So like I'm gonna try. I'm building all of the proof automation first. I'm building all the proof automation first. And the thing is proof automation can only go so far. Here, right? Because for example, I use this tactic called BV decide. BV decide is a SAT solver. Um, you see this stuff? This can be turned into like a bunch of propositional logic. This can be turned into a bunch of like propositions. Um, for example, this is like a bunch of like this is like bits, 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 true and false, and like that. This is like propositional logic. Uh, Using BV decide, you can prove this. But what if you want to prove it for all bit widths, right? You can't run a proof for bit width 1, bit width 2, bit width 3, bit width 4, bit width 5, bit width 6, all the way up to infinity, because this is like an infinite amount of bit widths. Like you need to prove this like for all bit widths. You can prove this for 32 bits, right? But to prove this for all, like you can't do that automatically using this stuff. You can't prove it automatically. Um, so what you need to do is you need to use like some like higher theorem, some like higher solvers, like that don't work, that like can prove for all bit widths, not just one bit width. Or you have to make a human do it, right? And I really, really don't want to have like 10 different, like 20 different theorems where, like, okay, I'm going to prove it for bit width 1. I'm going to prove it for bit width 2. I'm going to prove it for bit width 4. I'm going to prove it for bit width 8, 16, 32, 64, 128, right? I don't want like 5 copies of the same theorem. I want to prove it for all bit widths. So like you can't use BV decide. You can't use this decision procedure. What this does is like it just proves anything with bits. Anything with bits, it proves it. But it can't prove uh it can't prove anything with bits when you don't know the bit width beforehand, because it has to construct all of the bit boolean expressions. So if this is unknown, if you want to prove it for all n, you can't. So you need to use like you got to get a human to do it, or you can use like grind, but grind doesn't work like all the time. Like grind just doesn't work. Grind like just can't do this. Um, so you got to make a human do it, and like that's what I need to do. That's like I need to make a I need to get a human to do this. Like for example, a hard proof for all of the there's no way I can like automation do this, but like a hard proof would be something come on, where is it? Hard proof would be a hard proof would be like this, right? Can you reassociate these? I guess it's true, but this can introduce undefined behavior because if you reassociate the brackets, right, you move the brackets around, you're changing where undefined behavior happens, right? An example of this is like, okay, you have huge plus small plus negative small, huge plus small plus negative small. So for example, right, this happens first. This is UB because it overflows. And this is UB. But if you reassociate the brackets, this is just 0, and then that's just not UB, right? You can't reassociate the brackets because you change where UB happens if UB happens or UB doesn't happen. So like this is like hard to prove. So the only way you can prove it is if you have this assumption that they're all the same sign, or yeah, they're all the same sign. That's like the assumption you need. And like to prove the resulting theorem given this assumption is like really like fucking annoying. If I want to prove it for all bit widths, I cannot use my existing automatic infrastructure. I can't do the automatic stuff. Yeah, I can't do the automatic stuff. So I'm just stuck. So I need to do this, right? I need to do this. I need to solve. I need to make it nice for humans to do this. Then like the more I add, the easier it is. So I guess before Friday's stream, before Friday, I need to like work on that a lot. Anyway, yeah, I think that's it. I think that's it for reals, for reals. I need to have lunch. Yeah, true. Oh, I'm so hungry. All right, goodbye. Goodbye, everyone. Thanks for showing up.